So in this tutorial, we're going to introduce a specific type of climate model ensemble that can be used to understand and quantify internal climate variability. Now we know that the simulated climate in any of the CMIP6 models or other climate models that we use is not exactly the same as Earth's climate for several reasons that we're going to talk about today. Now, the first reason that we're focused on in this tutorial is because internal climate variability, which is a source of uncertainty that arises from the physically complex and chaotic nature of the governing equations for the evolution of the Earth system and its components. And what this variability essentially means is that small changes in initial conditions or forcing of the system can lead to significant changes in the future and instant time. Now, this is akin to the butterfly effect, where you think about a butterfly flapping its wings in one location could seed the perturbations that allow a weather event like a hurricane to develop far into the future in another location. And internal climate variability is the reason why there are certain events like weather events, storms, El Niños that can't be predicted far in advance. Luckily, we can use climate models to quantify the amount of uncertainty that is coming from internal climate variability by using what we call a single model ensemble, where we run the same model, for example, CESM, repeatedly, but each time we run it, we add slight variations, perhaps changing the initial conditions slightly or changing the forcing slightly. And the differences between all these model simulations within this single model ensemble can tell us about internal climate variability. Now, these single model ensembles are already a part of CMIP6 and prior CMIP experiments. And actually, when you were loading data last week, you used ensemble member parameter that identifies which member of the single model ensemble you're taking data from when you analyze CMIP data. And that was called the member ID. And it consisted of 4 letters, with each letter associated with a number. So that first letter, R, stands for realization. All of the historical simulations in CMIP are initialized from a spin-up simulation of that model that might be run for hundreds to thousands of years until it equilibrates before starting the 1850 historical simulation. So these realization members of single model ensemble could be started from slightly different years of the spin-up simulation. For example, one might start with year 600 and the other year 601. The second letter, I, stands for initialization. So we can run a set of models with the same initial conditions with the random noise added to each of those initial conditions, so they're slightly different. Now, the third letter, P, stands for physics. So we can adjust the parameterization or the representations of physics and which physics we include in the simulation and between ensemble members. And the final letter stands for F, forcing, which essentially we can use slightly different forcing time series details for each single model ensemble member. Now, like I said, CMIP includes these single model ensembles. In CMIP6, there are several models that have their own single model ensembles. For example, CESM, which I've already worked with, as well as the GFDR and Max Planck Institute Earth System models and the Canadian Earth System model. And what you're going to be doing in this tutorial is using one of these single model ensembles to assess how much internal climate variability contributes to modeled uncertainty.